Welcome to this deep dive into Secure Onboard Communication, or SecOC. Today, we're going to look at the functional specifications and the integration details specifically for the AUTOSAR Classic platform. Our main mission with SecOC is to verify the authenticity and integrity of sensitive vehicle data without clogging up the communication bus. Instead of using heavy asymmetric signatures, we use a symmetric approach with message authentication codes, MACs, making it perfect for legacy systems like CAN and FlexRay. Architecturally, the SecOC module sits right between the PDU router, PDUR, and the Crypto Service Manager, CSM. Think of the PDUR as the hub that routes messages to us for processing, while the CSM acts as our engine for cryptographic primitives like AES, CMAC. To trust our data, we rely on three pillars. First, we confirm the message actually comes from the correct AQ. Second, we ensure it hasn't been tampered with. And third, we use freshness to stop replay attacks, where an attacker tries to resend a valid old message to trigger an action. Let's look at the anatomy of a secured message. It starts with an optional header for length, followed by the actual data payload. After that, we append a truncated freshness counter and finally the MAC, or authenticator. Together, these pieces form what we call the secured IPDU. To save bandwidth, we don't send the entire freshness value. We keep the most significant bits local on both sides and only transmit the least significant bits. The receiver then uses its local counter to reconstruct the full value for verification. The secret to the MAC's security is what goes into it. We concatenate the data ID, the authentic payload, and the complete freshness value before running them through the AES CMAC algorithm. Even if we only transmit a truncated MAC, the calculation always uses the full freshness value to bind the message to a specific point in time. When an AQ sends data, the PDUR hands it to SecOC. We query the freshness manager for a value, ask the CSM to generate a MAC, and then bundle everything into a secured IPDU. Only after this, wrapping process is the message sent back to the PDUR for actual transmission. On the receiving end, it's all about verification. We pass the incoming PDU, reconstruct the full freshness value using our local manager, and then ask the CSM to verify the MAC. If they don't match, we drop the data immediately to protect the application. In the real world, the CSM or freshness manager might be busy when we need them. SecOC handles this with a retry loop. We'll attempt to build the authentication information a set number of times, and if we still can't, we can send a default, dummy, pattern to maintain system timing. What happens if a receiver misses a few messages? Their local counter falls behind. To fix this, we use an acceptance window. If the received LSBs are within a certain range, the receiver can jump its local counter forward to get back in sync with the sender. Here's a great way to optimize. If your payload already includes a unique counter, like an E2E counter, you can configure SecOC to extract that and use it as the freshness value. This completely eliminates the need to append extra bits to your frame. For those of you implementing this, you'll spend most of your time with these APIs. We have SecOC_ init for setup, SecOC_ if transmit for sending data, and the main function calls that handle the periodic scheduling of RTX and RX tasks. Don't get tripped up by data layout. All data transmitted over the wire must be in big endian format. Also, when you're passing freshness arrays to the API, they must be MSB aligned, meaning a 10-bit value is padded with zeros at the end, not the beginning. To wrap up, SecOC gives us a standardized way to secure vehicle data. It's highly flexible, allowing us to scale from full 128-bit MACs down to highly truncated versions for narrow bandwidth buses, all while ensuring that different vendors' AQs can talk to each other securely.